In this problem, we're given the function f of x equals 4 over x squared plus 4, and we've been asked to find only the relative minimums and maximums. This occurs whenever the first derivative equals 0. So, using the quotient rule to find the first derivative, the quotient rule is the derivative of the numerator, in this case 0, times the denominator, minus the derivative of the numerator, in this case 4, times the derivative of the denominator, in this case 2x, all over the denominator squared. And when we simplify this, we find that the first derivative is equal to negative 8x over x squared plus 4 quantity squared. This function will equal 0 whenever negative 8x equals 0. And this occurs when x equals 0. So I could have a relative min or maximum at x equals 0. I also may have some issues whenever the denominator equals 0, but in this case the denominator will never equal 0. So we're safe there. So the only thing we need to test then is what's happening before and after 0. I'm going to test the numbers -1 and +1 to do my sign analysis. When x is -1 in the derivative, we would get 8 over some positive number, which means that the derivative is positive before -1. When we test +1, we get 8 over some other positive number. So there are no minimums or maximums for this graph because although the derivative equals 0 at x equals 0, it does not change sign there. Let's consider our final example. We've got an airplane that's starting its descent when it is at an altitude of 1 mile, 6 miles east of the airport runway. So, one thing we know is that it's at a height of 1 when x is 6. So something about this function is that f of 6 equals 1. We need to find a description of the movement of the plane in terms of its descent. Is it going to be a cubic? And we'd like to find the location where the plane is descending at the fastest rate. Well, so f of 6 equals 1. A couple things. We know that if this is a cubic, then it will be of this form, plus cx plus d. We know that its derivative will be equal to 3ax squared plus 2bx plus c. We also know that when the plane is at the airport, or when x is 0, then its altitude will be 0. And finally, we might consider the second derivative. We know its form will be 6ax plus 2b. How does this help us? We do know that since it's starting its descent at x equals 6, that means it's just flying, it's not descending before that. So this tells us that the value of the derivative at 6 must equal 0. So a couple things then. When x has a value of 6 in the derivative, then the whole function should equal 0. So one thing that's true is that 0 equals 36 times 3, which is 108a plus 12b plus c. And so that much we know. If f of 0 equals 0, that means that when x is 0, this entire thing should equal 0. So that does mean that d must equal 0. Because if x is 0, then everything else will drop out. That means that there is no constant involved initially, which is nice to know. If f of 6 equals 1, then, at least from the original equation, what we know is that 1 must equal, when I substitute 6 in for x, 216a, and 6 plus 36b plus 6c. And the final thing that I know is I do know that f prime of 0 must be 0, because once the plane is on the ground, it will not be descending anymore. This means that c must equal 0 as well. And so this helps us attack the problem, because now both of these equations turn into systems of equations. 0 equals 108a plus 12b, and recall that this came from just knowing some things about the derivative. Second, we know that 1 must equal 216a plus 36b, and this is a system of equations that I can solve. Multiply the top equation by 3. That will give me 0 equals 324a plus 36b. And when I subtract these, I'm going to find that 1 equals negative 108a. So a must equal negative 1/108th. So I know D, I know C, I know A. Now I just need to go back and find B. And if I substitute back into this equation, with A having a value of negative 1/108, then this will become negative 1 plus 12b, or 1 equals 12b, or b should equal 1/12th, which tells me that my cubic should be f of x equals negative 1/108 x cubed plus 1/12 x squared. And if you graph that, you'll see a very smooth curve. Finally, we are asked to figure out where the plane is descending the fastest. And the plane will be descending the fastest when the first derivative has a maximum. Well, we know the first derivative will have a maximum. So if we consider the first derivative over a function, it will be negative 1 over 36 x squared plus 1/6 x. We want to know, when is this going the fastest? When is it descending at the fastest rate? Well, since our original function is the position function, then the derivative is the velocity function, telling us how fast it's descending. And this will have a maximum whenever the second derivative is equal to 0. So if we consider the second derivative, this would be negative 1/18 x plus 1/6. So again, the question is, when is the plane descending at the fastest rate? Or what is the maximum speed or velocity of the plane? Since the derivative is an expression of the velocity of descent, then this function's derivative will tell us where there is an extrema. This function equals 0 when negative 1/18 x equals negative 1/6, and this occurs when x equals 3. So this is the location of the plane, right? It's 3 miles away from the airport. And if we wanted to figure out how high the plane was at that time, we could just go back into the original function. And that is it for function analysis.